Bismillahirrahmanirrahim. Assalamu alaikum. In this session, we are going to talk about the fractal nature of network traffic. We're going to see how network traffic demonstrates self-similarity and long-range dependence. We're going to see how these properties affect network performance evaluation. To get things started, let's talk first about the difference between voice networks and data networks. So when I say data networks, I'm talking about the internet and the technologies that drive the internet. Before that, before the creation of the internet, there is a long history of telephone networks. And the techniques that apply well to telephone networks are very well studied. This is because the traffic of voice networks are also amenable to mathematical analysis. So we can say that telephone traffic is easier to treat than network traffic. Network traffic is more messy because of reasons that we would see in today's session. So what is the reason that telephone traffic is more tractable? The reason is telephone traffic is more predictable. It is more homogeneous because of many physical constraints. If you recall, when we talked of mild randomness, we gave an example of height, and we said that there is a physical limit which constrains people from growing to very, very extreme heights. So typically you would have heights that are close to the average value. You can also talk about mild randomness in telephone networks. In telephone networks, we can predict a lot about the usual behavior of users. So there are physical limits as well as to how much someone can speak, how quickly someone can speak, and also psychological reasons. So how much would you want to talk to someone? How much would you withstand or bear someone talking to you? Obviously, you cannot talk to someone for days on end. But this is in contrast to data networks. In data networks, you do not have to talk to someone per se. You can send a very large file. And in the length of the file, we have huge diversity. You can have a very small file. You can have a very large file. And typically, for the modern world, the data networks that we have currently are used to carry multimedia traffic. And because of that, the size for a multimedia file would be very large, and the file size for a text file would be very small. Also, you have huge diversity of the connection speeds. Someone might be connecting to the internet at an uplink speed of some kilobits per second, while others can be practically connecting to the internet at very high speeds, maybe multi-megabits per second or even gigabits per second. So because of this diversity, we can say that data network belongs to the world of wild randomness, in which the randomness is on very wide scales, on many orders of scale. So when we talk of the telephone network, the traditional approach has been based on Poisson and exponential modeling of the number of calls and of the inter-arrival call times, respectively. So these things have worked well because the traffic that is carried on telephone network is particularly easy to analyze, and the assumptions that we've made are actually confirmed by the kind of traffic we're moving. But the Poisson and exponential approximation is not very accurate when we talk of data traffic, because data traffic has very wild randomness. So if you recall, we talked of the world of power law distributions in which you have infinite variance. The world of telephone networks is well modeled by theories coming out of the bell-shaped world of mild randomness. But for data networks, we need theories coming out of the world of wild randomness or the world of power law distributions. So it has been shown in many repeated studies that Poisson approximations do not model the internet well, except for some very few properties. And for most of the properties, you require heavy tail distributions, and your traffic is self-similar and demonstrates long-range dependence. We're going to cover these concepts in this session, but let us first of all elaborate very briefly on what long-range dependence means. So long-range dependence actually defies the common assumption that arrivals are not related to each other. In fact, if we have a long-range dependent process, the correlations between successive arrivals is not negligible. In fact, the correlations exist for very far off arrivals, leading to very messy analysis. So let's study the kind of burstiness that we have in data networks by adopting a few terminologies that were proposed by Mandelbrot in his work that analyzes finance. We've already mentioned that the studies into randomness of finance has much in common with the randomness we have in data networks. This is because of the parallel between, we've seen the example of wealth, which has no physical constraints, and the data traffic also does not have many physical constraints, and because of that the randomness is very similar. So it serves us well to study how randomness is studied in the world of finance. So to illustrate this, Mandelbrot has coined two terms. So these terms are the Noah effect, which is titled after Hazrat Noah alayhi salam, and Joseph effect, which is titled after Hazrat Yusuf alayhi salam. And because these are also biblical prophets, he is borrowing from his own background as well, because the Old Testament also mentions these prophets. So the idea is, when we talk of the Noah's effect, is that you may have infinite variance. You may have some event that is so different from what you have been experiencing that it is calamitous. So this explains the very sudden shifts. So in financial world, you have, for example, in the stock prices, general low level of volatility, and then you have a sudden jump, a catastrophic event. And this is what we mean by infinite variance. You have, for example, a jump that is of many magnitudes of standard deviation. As an example, you have a drop of 20 standard deviations. So if we consider the normal bell curve, such an extreme event is going to never happen practically. The probability of this is something of the order of 1 over 10 raised to 50, something that is not going to happen in the life of this universe. But these kind of events happen quite regularly, too frequently for the comfort of all of us. So because of this, in the financial world, Mandelbrot has suggested that you need to cater for such very wild jumps. In fact, you would be surprised to see that even in the financial world, you have very simple models that are Markov based, or they belong to the world of bell-shaped randomness. But the real financial world, like the world of network performance, is having wild randomness in which you have very wild jumps. So these wild jumps are characterized by the Noah's effect, which says that you can have very calamitous change in the values that you have, and this extreme value is going to change your average for a long time, or it is going to have a significant effect on your average statistics. Another artifact of the world of wild randomness is what is known as the Joseph effect, in which you have long-range dependence. Traditionally, we have been assuming that every event is independent of all other events. However, if we consider long-range dependence, the occurrence of an event actually affects all events that are going to happen after that. And typically we have persistence. So if you consider the story of Hazrat Yusuf alayhi salam told in the Quran, you would see that the Prophet prophesied of 7 lean years followed by 7 years of plentiful resources. So the idea here is that you have certain amount of persistence, and because of that, the high values that you're going to get is more high than what you would expect from the bell-shaped world. And the low values that you are going to get is going to be more extreme than what you would expect from the bell-shaped world. So because of this, if we combine both of these properties, you're going to have sudden shifts, and you're also going to have persistent behavior. This actually neatly captures the financial world and also the network performance world. We're going to see that even for network performance studies, when we consider network traffic, you have persistent behavior to a certain extent. And you also have extreme events that have very low probability in the bell-shaped world, but they have a non-negligible probability if we consider the world of wild randomness. If you see on the slide now, you would see two images. So the bottom right image that you see is an image of the Aswan Dam built on the River Nile in Egypt. And this is the background in which much of the research into long-range dependence was initiated. In fact, you had a British hydrologist called Hurst who actually researched into the average levels of River Nile. And he was doing this to discover what is the optimal height of the dam that they want to build. So he discovered that River Nile has long-range dependence, much like the Joseph effect that we've talked about, in which you have periods of persistent drought and then you have persistent plentiful years. So because of that, he came to the conclusion that you would need to build higher dams with higher bank levels. And that was because when you have persistent plentiful rain, you're going to find that the river is going to flood. And because of the persistent long-range dependent behavior of River Nile, these banks have to be higher than what you would predict from the world of mild randomness. So if we take into account long-range dependence, you need higher bank levels. The analogy to network traffic is that because network traffic is also in many cases long-range dependent, you need to have bigger buffers, because like it is a straightforward analogy. The bank levels are there to store the water so it does not flood. In the case of a network router, the buffers are going to store the packet so they may be processed. Let's talk now about self-similarity in network traffic. But before that, let's play a simple game. I'm going to show you two images, and one of these images is an actual image, an image of a mountain range. The other image is a computer-generated forgery. So I am going to ask you to differentiate and pick out the fake one. So do you get an idea of which one is the fake one and which one is the true one or the real one? It looks very similar, and I'm actually not going to give you the answer because there is uncertainty here, and I want you to resolve this uncertainty by going onto the internet and looking this up. The person who has created the forgery, his name is Ken Musgrave, and you can look up his work and you would be able to see, maybe find the same image, and then you can tell me, maybe discover for yourself which image is the real image and which image is the fake one. But the point I'm trying to make is, when we're using models, we want our output or our model to be indistinguishable from reality. And if the approximation is very good, you would find that your model actually gives results that are very close to reality. It would never be the same, but a very good and close approximation. If we extend this further and analyze a time series now, you would find 4 time series shown on the screen now. So they look pretty much the same. Can you see any difference between these 4 time series? To me, they look practically the same. The reason is the way they are drawn. In fact, in these 4 time series, you have 2 actual time series of a random process, and you have 2 computer-generated forgeries. In other words, you have data that is created from a computer model. So a mathematical model is describing that process, and for the other two processes, it is the actual real process. So again, the question is the same. Can you spot the fake ones from the real ones? From these figures, it is hard to actually spot the fake. Let's transform this, and instead of showing the actual time series, let's have a look at the difference between successive values or successive instances of time. Now you can observe some difference. For example, the second one seems to be different from the other ones. So like odd man out, this is a little odder than the other ones. You would say that this is a little different. This is in fact because the second graph is generated from the model of random walk, which belongs to the world of mild randomness. It belongs to the bell-shaped world. You would see that the difference is pretty homogeneous. You don't have very drastic shifts. So we can easily make out that this is different from the other time series, and this highlights the deficiency of the models that are based on the bell-shaped world when they're used to model financial data or network data. So the other three look almost the same. So let's now analyze the other three. The top graph and the third graph are actual real-time series. The first one is the IBM stock prices from the years 1959 to 1996. The third one is the exchange rate between dollar and Deutschmark. So for the fourth one, it is a model-generated time series. In fact, this is generated from one of the models proposed by Benoit Mandelbrot. So if you observe, this model is a good approximation of reality or of real financial processes. In our cases, fractal models are good approximations of network traffic. Let's see some evidence of that. On the screen now, you find what you would expect from values created from Poisson model. In Poisson traffic, you have some burstiness, but that burstiness is at the scale at which you've defined the Poisson parameter. So if we observe the figures, the top figure has some burstiness. But if you keep on increasing the scale, so the top graph is between 0 and 6. If we further look on to this process at a higher scale, we see that between 0 and 60, the features of the time series are generally becoming less pronounced. You have a smoother version now. And if you keep on this aggregation, you would observe that at a sufficiently high level, you would see that now the time series is practically smooth, and the burstiness is all gone. So now we want to see if this is a true model of network traffic. So let's see a trace of network traffic. This is, by the way, a study done by Leland and his team, Walter Willinger and all. They performed this study in 1993, where they inspected and evaluated and examined the traces of Ethernet traffic. So this is what you would expect from Poisson-generated traffic. If the Poisson model is a good approximation of reality, you would expect that measured traffic would be like this as well. So let's have a look at measured traffic now. Measured traffic is bursty at the smallest scale, like Poisson traffic. But at higher scales, we see something very interesting, which is different from what we are seeing in the Poisson-generated time series. You observe burstiness at all different time scales. Even at the highest scale, you observe that there is still burstiness. So it shows that Poisson model is not a very good approximation of measured traffic. So how do we go about modeling measured traffic then? So a good model is a fractal model in which you have burstiness not only on one time scale, but on all different time scales of interest. So you would recall from previous session in which we talked of fractals and their property of self-similarity. And when we talk of fractals having statistical self-similarity, they have the same amount of burstiness at different scales. And that is exactly what we want. So a fractal model is now demonstrated, and you see a close match between fractals and measured in a distributional sense, or in the amount of burstiness that you see. So this is again like picking the fake. If you see the two images, they are now almost identical. They look very similar. So the fractal model and the measured model, the measured readings are actually in close sync if we talk of statistical similarity. And a fractal model in general is better than a Poisson model in modeling the roughness of real processes, because real processes have burstiness at different time scales. Okay, so let's proceed further and see how we can establish self-similarity. So for that, let's see the concept of aggregation. So we will study this through an example. So you see on the screen now a made up time series. You have some value. Each value is for a particular instance of time. Okay, so we want to aggregate this time series now, and the aggregation level is m is equal to 2. So if we want to do that, we're going to take two successive values. We're going to take the average of it, and we'll keep that as the value in our new time series. So the new time series where m is equal to 2 is going to have half the values of the original time series, and it is going to be aggregating the values of the original time series. If we take the example of m is equal to 5, we see that you have further more aggregation. In general, we can say that a time series X is self-similar if its aggregated version also has a similar distribution that is scaled by a factor of m raised to h, where m is the aggregation factor and h is the Hurst parameter. So we'll be seeing that this parameter h is very important in the analysis of self-similarity and long-range dependence, and it is a single scalar parameter that can define both of these quantities. So when we say that the aggregated time series has similar distribution as the original time series, we mean that the mean, the variance, and the autocorrelation has similar, identical, or similar properties. So if we have exact self-similarity, then you would have identical distributions that are scaled. But if you have asymptotic self-similarity, then this relation would be established in the limiting sense. So let's have a look at the graph on the screen now, where you see the autocorrelation function drawn for different lags. We've already seen what correlation is, and that tells us how two sets of values are related or how they move in sync. You would have a higher correlation value close to +1 when both of them are positive at the same time. So a positive value on one set corresponds to a positive value on the other end, and vice versa. But when we talk of autocorrelation, we are actually checking the correlation of the time series against the same time series, but that is time shifted. So for different values of lag, we see how much of an correlation exists, and it actually helps us to pick out periodicities in the time series. So you can see on the graph now that two lines are shown, and the first line is the original self-similar process, and the other line is the aggregated self-similar process. You can observe two things from this graph. The first thing is that the level of decay is not very steep. So because of that, you are decaying very slowly, both the original time series and the aggregated time series. And the property of our interest is that the original time series and the aggregated self-similar series have very similar properties. They are decaying in the same manner. So this actually helps us to provide evidence that the time series is self-similar, because even on aggregation, the autocorrelation remains the same. This can also be demonstrated by calculating the variance of the aggregated time series and how it varies with different values of m. If you recall, m is the level of aggregation. If you note carefully, when we're doing aggregation, we're actually taking the mean. And we've already studied the sampling distribution of the mean. So if you recall, we have a graphic to represent that. You see that the sampling distribution of the mean has some variance. And this variance is related to the variance of the original population. If the original population had variance of sigma square, the sampling distribution of the mean would have variance of sigma square divided by m. We also covered the same for standard deviation. When we talk of standard deviation, the standard deviation would be sigma divided by under root n. But currently we are interested in how variance is affected by the level of aggregation. So if we think of this, we can say that the variance of the m aggregated series is equal to the variance of the original series divided by m. But this is different for a self-similar traffic, and the relation then is variance of the aggregated traffic is equal to the variance of the original time series divided by m raised to minus beta, where beta is in the range of 0 and 1. It is more than 0 but less than 1. In other words, it tells us that the variance is going to reduce, but not as swiftly as we would have for non-self-similar process. In a self-similar process, the variance reduces at a much lower rate. So you can see this on a log-log plot, which is shown on the right-hand side of the screen now. The y-axis is showing the variance of the m aggregated time series. For the x-axis, we have the aggregation level, and both of the axes are logarithmically scaled. So you would observe that if we consider a non-self-similar process, it is going to decay at a slope of minus 1. So if you increase the sample size, the variance is going to reduce, and at a rate of 1 over m, or the slope that you have is having a value of minus 1. But if you have a self-similar process, the variance decays at a very low rate, much lower than what you would expect for a simple process that is not self-similar. In fact, the slope of decay for a self-similar process is minus beta, and we've already covered that beta is a value which is more than 0 but less than 1. There is an alternative formula for this as well, which relates the value beta to the Hurst parameter. If you recall, we just mentioned that the Hurst parameter is a single scalar parameter that can define both the self-similarity and the long-range dependence that we would cover subsequently in this session. The formula is the variance of m aggregated x is equal to the variance of x multiplied by m raised to 2h minus 2. This h is usually a value between 0.5 and 1. When you have a value of more than 0.5, you have an indication that the process is self-similar. If you have a value of h is equal to 1, then it is exactly self-similar. So with this, I hope the idea that how beta and h are related has been demonstrated. Okay, so let's now talk about long-range dependence. So before we get down into the details of long-range dependence, let me make a clarification of how self-similarity, long-range dependence, and heavy tails are related. The differences are subtle, but it would serve us well to first of all note what these terms actually mean. So when we talk of heavy tails, we can think of a distribution in which the tail of the distribution is decaying like a hyperbolic function. So very, very extreme values still have some non-negligible probability. In the domain of actually seeing the samples, if you see the bottom figure on the left hand side, you would observe that most of the values are quite small, but then you have some huge values. That tells us that extreme values do occur. So heavy tails are useful when we want to model the world of wild randomness. So heavy tails serves that purpose. When we are talking of self-similarity, the main thing that we are concerned with is that when we scale the signal in time, are the properties of the new time scale signal similar to the original time series? If it is, then our time series is self-similar. And we've mentioned of second order statistical self-similarity, when the time scaled or the time aggregated series has similar mean, similar variance, similar autocorrelation function that may be scaled, but still it is very similar. This can be defined in the sense of exactness and also of asymptotic, where this relation holds in the limiting sense. And also we come to the point that we want to discuss now, long-range dependence. And long-range dependence actually has to deal with the autocorrelation function. So if you remember, we just mentioned autocorrelation function measures the correlation of the signal itself with the signal at various time lags. Now if your autocorrelation function does not decay to zero very soon, that tells us that the current value is significantly correlated with previous values. This has many implications. And when your autocorrelation function decays like a power law, so you can see the power law shown on the screen now, and the signature of a power law is a straight line on a log-log plot. So if the autocorrelation function decays like a power law, we have long-range dependence. So the subtle difference comes when you have some processes that are self-similar but not long-range dependent. For example, Brownian motion has h value of 0.5 and it is self-similar, but it is not long-range dependent. But if you have the example of fractional Brownian motion, then your h value is more than 0.5 and you have long-range dependence as well as self-similarity. In general, and that would be the rule that we follow in network performance evaluation studies, usually both of them occur at the same time. If you have self-similarity, you also have long-range dependence, and long-range dependence produces self-similarity. So we can use them interchangeably in our field, luckily. One point I'd like to make is, for long-range dependence, the value of h has to be more than 0.5. But for self-similarity, you can have self-similarity if h value is 0.5, the case of Brownian motion. So I hope the subtle distinctions are a little more clearer. So let's move ahead. I will note furthermore that even heavy tails are related to the other properties. In fact, if you aggregate heavy tail distributions, it has been shown that you produce self-similarity. So all these three things are related, but it would be good if we can remember the distinctions between them. So as mentioned before, if we are talking of long-range dependent process, the signature of such a process is that the autocorrelation function decays like a power law. And you can see that on the slide now illustrated more. You see a typical function that is short-range dependent. You see that the autocorrelation function is decaying very fast. Let's say exponentially fast. And exponentially fast is, in most practical cases, the fastest decay that you can have. So if that is the case, you are going to have an ACF value which is going to come down very, very soon. And most processes, the short-range processes, have exponentially decaying autocorrelation function values. Poisson models have exponentially decaying autocorrelation values. But if we are talking of a long-range dependent process, and many traffic values are long-range dependent, then you would have an autocorrelation function that decays like a hyperbolic function. So you can see that on the screen now. And another practical import of this conclusion is that you would have non-degenerate autocorrelation. If your autocorrelation function is decaying like a power law, even at very, very large values, you would still have some non-zero value of the autocorrelation function. So this is counterintuitive, but this is how network traffic works. Very, very distant things happening in the past actually affect what is going to happen now. And what is going to happen now is going to affect things that are going to happen a lot later. And it is because of this reason that you have self-similarity. At very different levels of aggregation, you have burstiness. So all these things are tied together. Long-range dependent traffic can also be shown as illustrated in the graph on the right hand side. You would see that because the ACF, the autocorrelation function, is decaying like a power law, you would have a straight line if we plot both things on the logarithmic scale. Okay, so how do we actually establish long-range dependence? So another alternative method is by the use of rescaled adjusted range statistic, also known as the R/S statistic. And this has been proposed by Hurst, who we've mentioned was studying the water levels of River Nile. And River Nile is long-range dependent. The values of the amount of water that you have in dams is going to be is actually related to values that existed very far off in the past. So to illustrate this, he discovered something empirically, that he made lots of measurements, and he came up with an empirical rule which actually highlights the relationship. So he discovered that if you were to rescale the range, and we would make this precise very soon, and we divide it by the standard deviation of the time series, it behaves like a power law. So the expected value of R over S is equal to C n raised to h, where h is the Hurst parameter. So let's see how R and S are calculated. So for seeing how R is calculated, let's first of all define WK. So WK actually tells us how much of the values seen up till now differ from the expected average value. So if we are calculating WK, then we would take a sum of the previous values from x1 till the current value, and we would see how different it is from the average value. And we do this then for all values of k, and with this information we can calculate the value of R of n, which is the range, which is the maximum of WKs and the minimum of WKs. The difference is R of n, and we divide it by S of n, where S is the standard deviation of the time series. S square n is the sample variance. So this may seem a little abstract, so let's make it more concrete through an example. So you can see a time series on the screen now, and what we are going to do is we are going to apply the rule that we've just discovered, or we've just learned about. So for RS analysis with n is equal to 2, we actually do this for all values of n, but I'm going to show you limited cases, n is equal to 2 and n is equal to 5 as representative cases. You can do the same calculations for other values of n. So if we have n is equal to 2, you would have 10 samples of size 2. For the first block, so if you observe the orange block, which is on the left hand side of the time series, this box is covering the values 2 and 7. When we have n is equal to 2, we would take successive blocks of width of two numbers, and we're going to apply our statistics, which will be used to calculate the RS statistic. So for block 1, which has the two numbers 2 and 7, what is the average value? The average value is 4.5. Now we can calculate W1 and W2, and that is done using the formula on the bottom of your screen. So if we calculate, we get values of W1 as minus 2.5 and W2 would be 0. The last W usually is always 0 because the sum of all the values minus the what you would expect, k multiplied by what you would expect, is always going to come as 0. So if we now calculate the range, we would see that this comes to be 2.5. Range is the difference between the maximum and the minimum, and the standard deviation is 2.5. So the Rn over Sn statistic comes out to be 1. So we've followed a long route to calculating this R over S statistic, and we've done this only for one value of n, which was n is equal to 2. So we can do this for other values of n, and we do this for all blocks as well. So if you do this for n is equal to 5, you observe that for the first block, you get an Rn over Sn value of 1.76. And for the second block, you get an R over S statistic value of 1.5. So with all these calculations and the getting of all these numbers, now we are in a position to apply the Hurst empirical rule. And we do this by plotting on a log-log scale the RS statistic value against the block size n. If you observe for increasing size of the block n, you would see that the RS statistic is increasing. But for a self-similar process, it is increasing at a faster rate. So if we observe the slopes, the slope of the line that we are going to get is going to be between 0.5 and 1. And that actually is the value of h. If you recall the empirical rule that Hurst devised, it had an exponent of h, and it had the form of a power law. Because of that, on a log-log plot, we are getting a straight line, and the slope of which is going to tell us the value of h. And this is just an estimation. So we have other more quantitative rigorous methods of calculating h, but that would be outside the scope of this course. Let us now talk about the impact of self-similarity and long-range dependence on network performance evaluation, and how pervasive self-similarity is in network traffic. So we start by talking about Ethernet traffic on the LAN. So Ethernet is the most dominant LAN technology. It was discovered in the period between 1993 and 1995 that Ethernet traffic is self-similar. And you can see that you have various graphs shown on the screen now. And many of the graphs have similar statistical properties when we see the measured traffic. But when we talk of Poisson model, the burstiness dies down if we move beyond the characteristic scale of the burstiness. But a fractal model, as discussed, it can capture the self-similarity on different scale ranges. So the point which is relevant to the discussion now is that the measured traffic of Ethernet is self-similar. And in later work, researchers have shown that this self-similarity can be modeled by assuming that the users can act as an on-off process. And when they are in the on mode, so this is like a switch. When the switch is on, they are transmitting. And when the switch is off, they are not transmitting. If the transmission duration and the idle duration is governed by a heavy tail distribution, if you aggregate many of such processes, you would get a self-similar process. And Ethernet is just that, a self-similar process. The traffic measured at different time scales have a very similar look. Such finding was then extended to WAN traffic. And researchers, namely Vern Paxson and his colleagues, showed that even WAN traffic is self-similar in many respects. So you can see a variance aggregation plot in which the aggregation, if you keep on increasing the aggregation, the variance is decaying less steeply. And we said that that is one of the trademarks of a self-similar process. So let's talk about web traffic now. Mark Crovella and his colleagues have shown that even web traffic and the amount of requests generated, the amount of requests received are better described by heavy tail distributions. And they've also discovered that many aspects of web traffic can be better described by self-similar processes. So it seems that the model of the internet is best described by power laws rather than models borrowed from the world of the bell-shaped world. And this is in fact true for the topology of the internet as well. If we were to think of the distribution of the nodes and their connectivity as it was distributed from, let's say, a bell-shaped world, you would have similar sort of connectivity. But what we find in actual reality is that the nodes have varying amount of connectivity. There are some nodes that have very, very high connectivity, while most nodes have very low amount of connectivity. So for similar amount of connectivity, two graphs are shown. But if we observe the left graph, which is drawn according to a power law, this is a more truer approximation of how the internet AS topology looks. So AS here is autonomous system. So now let us talk and conclude this lecture by talking about implications of self-similarity on network performance evaluation. Traditionally, in network performance evaluation, we've used Poisson models. And Poisson models underestimate the amount of burstiness, especially for aggregated traffic. So one consequence of this is that the analysis that is performed on the basis of Poisson arrivals tends to be very optimistic, whereas real network traffic is more messy. And if you actually compare real empirical results against results what you would get from Poisson analysis, Poisson-based queuing analysis, you would find that the real results are worse off, or the analysis-based results are too good to be true, or they are too optimistic. This is primarily because the Poisson modeling is not adequate for capturing the roughness of network traffic or the amount of burstiness, especially at different time scales. And the amount of self-similarity also affects the performance. So on the bottom graph of the slide that you can see now, you would see that for various values of H, you have different values. So what is the queue size? If we consider some given utilization, the queue size would increase for higher values of self-similarity. This is because when we have a self-similar process, it does not smoothen even if we aggregate to a very large interval. And that is one of the sad part of networks. We wish it was Poisson, and it has served us very well for telephone traffic. Telephone traffic is very well modeled by Poisson traffic, but it does not suit well the data network environment, and we have to accept that and make better and more realistic models. So let us now see what happens when we have things are evaluated according to Poisson models. You would have underutilization and overutilization at different fronts, because we do not exactly know the place where things are going to smoothen out. And because of the burstiness, it is very difficult to provision for networks because they have burstiness at many different time scales. So this now concludes our discussion on fractal self-similarity as they apply to network performance evaluation study. I'll conclude by saying that network performance evaluation traffic that we usually see when we are evaluating networks is self-similar and also long-range dependent. And because of that, simple models that assume independence and assume burstiness that is only on one time scale, they are inadequate for modeling real networks. If we are going to use such simple models, we must realize their limitations and we must use them only as first approximations. And then we need to progress towards better models. And we need to realize that the results that we would be having with simple Poisson models are going to be off the mark. Also, we've seen that analyzing long-range traffic and self-similar traffic is messy. You need to do lots of mathematics and there are lots of details. We obviously do not have time to cover most of it. In fact, we've just scratched the surface. To actually perform research in this area, I hope I have conveyed the essence of it, but you would perhaps need to look up the literature. Lastly, I would be again iterating that Poisson traffic results are optimistic and we need to make more realistic assumptions, and then only we can make inferences about the network. So till next time, Assalamu alaikum wa rahmatullah.